all your work. So that agrees with the experiment. All right, so let's look at another example now. And now we have, again, a two-step reaction. And the first step is fast and reversible, and the second step is slow. So with those predictions of the mechanism, let's just go right through and try to solve for the rate here without going through all of the steps we did the first time and see if we can do this more efficiently. And again, this is a reaction with ozone, and depletion of ozone is a major problem that will be facing us, that has faced us, and will continue to face us in the future. All right, so let's first think about the rates of the individual steps. So the rate of the forward reaction here is going to be what? Just yell it out. Yep. K1 times the concentration of O3. What about for the reverse step? Yeah, it's like clear and then it gets mumbly. K minus 1 times the concentration of O2 times this concentration of O, which is an intermediate. All right, so let's look at the second step here. So the rate here is going to be K2 times this intermediate concentration of this intermediate O times the concentration of O3. All right, so now we know that this second step is going to be controlling the rate. It's a slow step, at least that's our prediction that we're going to write a rate expression based on. And so that's going to be our slow step, our rate determining step. And again, we're forming 2 molecules of O2 in this step. So we can have a 2 in there, and that the rate of formation of O2 in this last step, 2 times K2 times our intermediate O times O3. Are we done? Was it that easy? Are we done? No. Why isn't this finished? There's an intermediate. Intermediates will not be your friend in doing these problems. Yes, we have an intermediate, so we're not complete. We need to solve for O in terms of products, reactants, and rate constants. So we're not done. So we need to get rid of the intermediate. But now we can do that more simply because we've set this up that we have a fast reversible step followed by a slow step. So we can solve for the concentration of that intermediate in terms of equilibrium expressions. So if you haven't learned how to write an equilibrium expression yet, remember you need it for the unit on chemical equilibrium, the unit of acid-base, the unit of oxidation reduction, and here you need it again in kinetics, so definitely want to be able to write those for the final. So we can go ahead and write those. So for the first step, again, it's products over reactants. You can also express that in terms of rate constant K1 over rate constant K minus 1, and that's all equal to our big K, our equilibrium constant, K1. And so now we can solve